why we call this is the fundamental solution. For example, why we say u asterisk between x and xi. Why we call it a fundamental solution? Because it is the solution of this equation u asterisk of x and xi equal minus delta of x and xi. Why it is equal to minus delta of x and xi? Why we call it fundamental solution? Because it is the most fundamental problem. Sometimes you call it principal solution or fundamental solution of, or 2-point fundamental solution, or sometimes they call it free space Green function. This is infinite domain. This is infinite domain. That means it has no boundary condition. And we have point called x. We have any point called x, another point equal xi. At this point here, I have a pulse. I have a pulse with the Dirac delta. I have a pulse with the Dirac delta. Okay. As far as we have a continuous domain, we don't have a discrete domain like we have a grid of points like a truss or grid network or something like that. In this case, we will use the Kronecker delta. We'll use the Kronecker delta, and we use this in stiffness analysis, the unit load approach or something like that. But here we have a continuous domain. So the alternative we have, or the extension of the Kronecker delta, is a Dirac delta here, because we have a continuous area. So we put unit pulse in infinite domain, no boundary condition, nothing, and we compute the effect here. So the effect here direct, this is, you can compute it. There are several ways. I am going to give a lecture on this, how to compute fundamental solution. You can use Fourier transform, you can use a lot of things. It's very easy to compute it using Fourier transform on Mathematica or something like that. It will give you minus 1 over, as I said, of 2 pi ln r between x and xi. So why we call it fundamental solution? Because it's the solution of the most fundamental problem. We have just infinite domain with single pulse or single load or single potential or single something like that. Okay. The another question I have, you have your problem in infinite domain or something like that. This is the shape of the problem, but not my problem. This is the shape of the problem, and you choose 4 sources. You choose 4 sources. Can I choose more than 4 sources? Can I choose more than 4 sources? The question actually come from the simulation of the boundary conditions. Here you put u equals 300, and here you put u equals 0, and here you put q equals 0, and here you put q equals 0. So originally we simulated u equals 300 by single point, and here you simulated u equals 0 by single point. This is x1, and this is x2, and this is x4, as I remember. And you simulated q equals 0 along all of the side by point 1 x1, and here also I simulated by point x3. So I simulated the prescribed boundary condition on my boundary using single point, using only single point. Okay, so I have 4. So practically now I have 4 known values. 4 known values comes from where? From the prescribed boundary conditions. Okay, so I want to make use of them. So as far as I have 4 sources, 4 prescribed boundary condition, so I can rewrite my problem with 4 equations. So at least I'm going to choose 4 sources with unknown phi 1, phi 2, phi 3, phi 4. Actually, the value of the phi has the same nature as u. So practically you put over there a potential over there to give effect for this source. Okay, so can I choose more sources? You can choose more sources, but you still have the same number of prescribed boundary conditions. Can I choose more points, x points? Yes, you can choose more x points. You can run the same equation using Mathematica, write a small MATLAB code or something like that. You can choose 2 points along each boundary to simulate the boundary condition. You will get better accuracy. You'll get better accuracy. Actually, our problem is very easy because it's a linear problem. So because of that, only 4 points give very correct answer. So I have the right now. I have the right now to choose. I have the right now. I have to choose x points, more x points, more x points. This will give me more accurate representation of prescribed boundary conditions. For example, if I have the same problem now, if I have the same problem, this one u equals 300 and this one u equal to 0, and half of this area is insulated. So at this point here q equals 0 and here will give u equal to 100, for example. And here is still insulated at all of this side. All of these sides are insulated. Q equals 0. So now I have extra point. So I need to add x point here to simulate this area. I need to add at least 1 point to simulate this area. Okay? One of the greatest thing about this point, this method, is we don't have a problem in discontinuity. For example, if I have here u equals 300 and here is u equal 100, forget about the other two sides, but at this corner here, at this point here, point A, I have u equal 100. At the same point here, B, I have u equals 300. So this point is a point of discontinuity. Definitely, this point is a point of discontinuity. So at this corner, we don't know the value of u, whether it is equal to u 100 or 300. We don't know. Okay? In boundary elements, it is very hard to put single node in the direct boundary element. It's very hard to put a single node. Because of that, we use double node, or sometimes in easy way we use something called discontinuous element to do that. Okay, but in this point, actually it is discrete points. So we put point here and we put point here, and the difference between this point and this point will come in the normal. Here we have the normal at point A is different from the normal at point B. So when we compute the flux, will be different at these 2 points. Okay, because we can't compute the flux at the corner direct. So this is very, very important point, very important simplification. We will face this complication when we move to the direct boundary element or something like that. We have certain treatments for these techniques. The xi points. Can I have more xi points? Can I have more? Yes, we can have more xi points. But as far as we have more xi points, we will not have rectangle. We will not have square matrices, because remember, the system of equation here, the system matrix is U asterisk Q asterisk. This is mainly the number here are the number of prescribed boundary conditions. So actually the dimension of this matrix, the first dimension is the number of x. So we'll give it the nx points. The rows is the nx points. And here is the vertical numbers is the xi points. The number of xi points. These are the number of nx and this is the number of nxi points. Okay, so the dimension of this matrix is nx times nxi. times the vector here is the vector of phi, and this one, the dimension is nxi times 1 equal to the prescribed boundary conditions. We'll give it B, which is equal to nx times 1. Okay, so if I choose my xi's, we have more xi's, we have more x's, we will use what we call it least square technique to do that. But this is very easy. Mathematics or numerics is not a problem now. We can compare, we can come back to it when we talk about advanced formulation at the end of these lectures. Still, there is one thing we have to put it in our mind. Where shall we place sources? Where shall we place sources? This is very important. Where shall we place sources? The simple answer for this question is arbitrary. Is arbitrary at any place. Place your sources at any place. For example, run again the same problems that I gave it to you, and instead of place the sources away by 4 meters, place the sources away by 3 meters or 2 meters. You will get different intensities, but at the end of the day, as more as you put boundary points, as more as you put sources, you will end up to convergent results. Coming back to the recommendations that comes from Professor C.S. Chan and Michael Goldberg, they said, as far as you have Dirk condition, when you have Dirk conditions, that means you are prescribed, is much better to place sources near the boundary. And when you have Newman condition, the Newman condition, when you have Q is prescribed, is much better to put it away, to put the sources away. These are the recommendation of Professor C.S. Chan and Goldberg, Michael Goldberg, Professor Michael Goldberg. But according to my experience, it comes by numerical experiments. Knowing that as more as you increase number of sources, you will increase the dimension. You will increase the dimension of the UQ matrix. The dimensions are going to be increased, which will lead to L conditioned matrix. Will lead to L conditioned matrix. Where are the sources? And the placement of the sources and all of these type of questions are studied very well, and very recently, I believe maybe in the last year, Professor C.S. Chan published a paper to compute something called effective condition number. Effective condition number. I will brought it to you maybe next lecture. And he claimed that according to this effective condition number, he can get initial places for the sources. Actually, my research team now, we are solving Navier-Stokes equation using meshless technique, and we use this effective condition number. It is a bit hard because we have nonlinear terms. Okay. By the end maybe of this lecture series, maybe I will get some more intuition about how to use this effective condition number. I use it now, and I had a meeting face-to-face with Professor Chan to discuss this with him. And as far as I didn't experiment it by myself, I will not give a conclusion about it. But maybe after 1 month or something like that, I have some idea. Maybe I will give it to you direct.